what we did last time, we started the development of the high frequency treatment of circuit. And the first thing we did, we started looking at a generalized high frequency but first order system, namely a system that had an input X, an output Y, and it had only one energy storage element, right? Which could be an inductor or a capacitor, right? And then what we did, we abstracted it out. We basically called it, let's say, element C1, or it could be an L1. And then the rest of we took it out of the network. So this is a network with no dynamics. And as such, it basically presents, then this whole system has to become a first order system, because if that's the only energy storage element in the system, and then we did the derivation, so we are not going to redo the derivation of the transfer function. So the transfer function of this thing we saw in general was basically h of s, which is the ratio of the output to input in frequency domain. It's a generalized gain, can be written as h0, and these are superscripts, remember, these are indices. These superscripts are indices, they're not powers, the way in this part of the treatment. H1 tau s over 1 plus tau s, which you can also write if you factor the H0, the low frequency gain, in this form. You can write it as H1 over H0 tau s over 1 plus tau s. So this we derived last time, right? So we derived it. We made several different kind of like parts of this thing, and and what this does, it reduces the calculation of this transfer function to calculation of 3 low frequency parameters, right? Namely H0, H1, and tau, where H0 and H1 are what we call transfer constants, as opposed to transfer functions. So this is a transfer function, but this is a transfer constant because it doesn't depend on frequency, right? And a time constant in this case. In general, there will be multiple time constants, as we'll see later, but this is basically a single time constant. So what was H0? H0 was H when the value of the energy storing element, in this case C1, would go to 0, or let's say in this case would be equal to 0. And then H1 is basically the value of the transfer function, or the transfer function in general, when C1 goes to infinity, when this is infinite valued or this is 0 valued. If it was an L, it would be 0 valued and infinite valued too. Now, and in these superscripts in general are the indices of the elements that are infinite valued. So if it says H superscript 1, H1 means that element 1 is infinite valued. So later on, if you have H1, 2, it means that elements 1 and 2 are infinite valued. So get familiar with that notation. And if it's 0, it means that nothing is infinite valued, if the superscript is 0, right? So now infinite being infinite valued, it means a different thing for, or 0 valued, it means different things for capacitors or inductors, right? For a capacitor, being 0 valued means what? It's an open circuit, right? And being infinite valued means short circuit. Now, and for an inductor, it would be the opposite, right? Being 0 valued is being shorted, and being infinite valued is an open. So you should keep this in mind. So in general, we are either setting it to 0 or infinity. So that's what these mean. Now, and tau is the time constant associated with the circuit, which would be determined by the capacitor in this case, or what we call R0 or R10, because its capacitor is index C1. Now, and what is this R10? Is the resistance seen looking into those ports where the capacitor is connected, with all the independent sources, including the input, being 0 valued, being nulled, right? Meaning that if you have a voltage source here, you short it. If you have a independent current source somewhere inside, you open it, you do all sorts of things, and see what's the resistance you see across. So with these, but what you can see is that all 3 of these calculations are low frequency calculations, right? In the case of an inductor, this would be, of course, tau would be L1 over R10, because it's L over R, the time constant associated with the inductor, right? And for capacitors, RC. So these are the things that we did last time. And we started doing a few simple examples, mostly with the passive R's and C's. So now we are going to do a few more examples of how this is applied to first order system. And you can see that you can actually get a lot of information even from the first order treatment. And then you will expand it and generalize it to multiple capacitors and inductors and see how it's applied. And you see that once you learn how to use it, it's actually a pretty convenient and fast way of doing things. So as a first example, let's say, let's try to do a couple of actual transistor circuits, right? So let's first let's say we do a analyze. So let's just keep this here. Start a new one. So let's say let's say we are dealing with a source follower or common drain, or it could be a common collector or emitter follower, all kind of essentially the same topology. So the idea here is that if you have a source follower, you have a resistor here, you have essentially a source resistor in principle. You have it's driven with a voltage source, V in, and then this is connected to some VDD, and this is your V out. So, and this is R2, right? R1 and R2. So if you have this kind of circuit, and let's say for now we are only interested in, so let's say, and then the equivalent small signal model for this would look like this. You have the input, you have R1. If you use the T model, you have Rm. You have, let's say, it's Is, ground, R2. We have analyzed this circuit before, right? This is V in, this is V out. And so what is the gain of this circuit? And this is Is. What is the gain of the circuit? The voltage gain of the circuit, as is? Well, the first thing to answer is that you want to see if there's a voltage here drop across this R1, right? If it was indeed an actual classic MOSFET, what would this current be? That's 0. So what is the voltage across this guy? 0. So this voltage and that voltage are the same. So then if this voltage is Vi and this is Vo, how do you determine the relationship between Vi and Vo? It's the resistive divider, right? It's R2 divided by Rm plus R2. So that's your low frequency gain in case you wanted to know what it is. So well, that is one of the things we want to find out. But before we do that, let's see what capacitor we want to take into account. So for now, let's assume that this is the only capacitor we want to, let's say this is the CGS, but again, in general, to use a single letter index, let's use C pi. Let's call it C pi, kind of similar to what it would be in bipolar. It doesn't matter what we call it, because then if you use it as pi as the index, then you can have H pi and whatever, as opposed to CGS, then you would have 2 letters that you have to deal with. So this is what we are trying to analyze. We are trying to find the transfer function from this input to that output and see how it behaves. So there are 3 things we need to calculate. The first one we kind of almost did already. So the first one was H0, the low frequency transfer function, namely when this capacitor is 0 valued. When it's 0 valued, it is what? It's open circuited, right? So we already make that argument what the gain is, right? It's this resistive divider. So that transfer function is R2 over R2 plus Rm. How about H1? H1 is when this guy is, it should be H pi actually, in this case. H pi, right? Because it's the index of this guy, right? So H pi, when C pi is infinite valued, is what? When you basically you short circuit this, if I short circuit this, what is the input and output relationship? If this is short circuited, what is Is? Yeah, because this voltage is 0, right? So this is 0, so this doesn't matter, it becomes open circuit. What are you left with? You have only the R1 and R2, right? If I short circuit it here, you have a resistive divider, R1 and R2. Will look like that. If this is shorted, right? So this is the resistive divider. So what is the gain of this thing? It's R2 over R1 plus R2. Right? Now, and you can see these calculations are actually pretty straightforward. because you're short circuiting stuff, so you're taking stuff out. And then there's one more thing that we need to calculate, which is the resistance seen here, right? It would be, in our notation, it would be called R pi 0, right? So R pi 0 is the resistance that's seen by this capacitor when the independent sources are nulled. So when I'm nulling this being a voltage source, this has to become a ground, right? This becomes a ground. So what I'm left with, what we are left with is something like this. So we have R1 to ground, you have Rm, you have Is, you have R2, the current source, Is, and then you want to determine that resistance. If you don't know in general, how do you do that? You apply a Vx and measure Ix, the test voltage, and you measure the current, and the ratio is the resistance that you see in a small signal. So if we do that, let's see what we get. If I apply this is Ix, so this current is going to be Is minus Ix. This current is going to be what? What is this current? 0. The gate current is 0. So the current going into R1 is going to have to be Ix. So all of this current is going through here, right? So the key question is what is the, and then if it's Vx, what is Is? So Is is what? Because if this is the voltage Vx across resistor Rm, it's going to be Vx over Rm, right? Also, you can write it as Gm Vx, right? So that's Gm Vx. And what is this voltage? Yeah, Is minus Ix, which is basically, you can write it as Gm Vx minus Ix times R2. So it's that voltage. Now that, right? Do you agree that's the voltage across the resistor R2? That voltage plus this voltage, plus the Vx itself, is going to be this voltage. Because this is also connected to ground, right? But that voltage is Ix times R1, or R1 Ix, right? It's a very simple KVL I've written around here. Now, if you do that, it's a simple calculation. So you basically take this term and move it to the other side. So you get R1 plus R2 times Ix. And on this side, you're left with whatever has Vx, which is 1 plus Gm R2 times Vx. So now you have the ratio of Vx over Rx, Vx over Ix, sorry, which would be R1 plus R2 over 1 plus Gm R2. Okay? And then you can plug that into, so that's the resistance. That's the basically R pi 0 that we are trying to calculate. So it's R1 plus R2 over 1 plus Gm R2. So you have these three. In a way, you're already done, right? Because you basically you can plug that into the equation and see what it looks like, or you already can keep them this way. A lot of times we actually may end up keeping them this way because we know what they mean. But in this case, let's plug it in since we are still not completely familiar with the platform, and then let's see how it looks like. So if you plug it into that equation, then it says H of S is going to be this thing. I'm using the second form, the factored form, because that gives me the poles and zeros directly, right? And then I have to calculate the ratio of H pi to H0. So you can see the R2's cancel, right? So what am I left with? It's basically 1 plus R1 plus R1. No. So it's this divided by that. So you get Rm plus R2 divided by R1 plus R2 times the time constant, right? Right? Times this time, times R, the tau. But the tau is this times c. But you can see when you multiply this and that, what do you get? These guys cancel, right? So I'm going to write it explicitly in this time. just so you can see it, but in general, we may jump that step. S divided by 1 plus whatever, R pi 0 C pi S. I'm just going to write it, keep it in that form. So what do we get? Well, these guys cancel, obviously. So you will end up with something like an R2 over R2 plus Rm. Again, some of these steps may not be completely necessary all the time. So what happens here is that, of course, this is that, but you can simplify this because you can multiply both the numerator, the denominator by Rm. So you get Rm plus R2 in the denominator. That cancels this Rm plus R2. So all that's left is going to be Rm C pi S divided by 1 plus R pi 0 C pi S. Right? So it simplifies to that. And then what you see from this is that there's a 0 and a pole. Right? Where is the 0? The 0 is roughly around Gm over C pi. Well, it's not roughly, it's exactly a Gm over C pi. And then, and the pole frequency is 1 over, well, negative that, and the negative here, R pi 0 C pi. And if you look at that, you can also rewrite this as, so if you look at R pi 0, you can do the same thing here. You can write as Rm times R1 plus R2 divided by Rm plus R2, if you want to write it that way. And you can use either one of the forms. That's fine. So the key point from this discussion is that you are getting a pole and a 0, both left half plane. And what happens to these two? If you look at these two and pay attention to them, you will see that you're starting from something and then you're basically ending in somewhere else. So what is the frequency of this thing? Do you think it's low, high, this 0 frequency, the frequency of the 0? What order of magnitude is it? Do you remember what Ft was? Ft of the transistor, when we calculated it way back? If you had taken both C pi and C mu into account, it was Gm over C pi plus C mu, right? It was omega t, really. It has a 2 pi there. But so you can see this is actually, if you ignore C mu, which we have, this is around the Ft of the transistor. It's a pretty high frequency. How about this one? Well, let's look at this number. It's Rm times this R pi 0. It's Rm times this thing. Now, if R2 is much larger than Rm and R1, then that thing is around 1. If they're on the same order of magnitude, they're also going to be, if they're around the same, also this is going to be around 1. So you have a pair of poles and zeros, right, that are present there, and you will get what you get, right? I mean, so you have a certain transfer function, and both of them, the pole and zeros that come out of this thing, are about the same, on the same order of magnitude. So this basically what it shows you is that this stage, at least in this form, if you don't include the C mu by C, just the C pi, is going to be pretty wide band. Right? It's a pretty wide band stage. And you will see, we'll do the C mu later. We'll add the C mu in there and see what happens when you introduce the C mu. But it gives you some sense for this. Now, these general calculations, you don't want to be doing this every time, right? And that's why there are those calculations that you did as a homework problem a while back, right? So I'm just going to refresh your memory on the results of those. You remember, in general, if you have a, let's say, a transistor, it can be a MOSFET or bipolar. So I'm just showing it as a general transistor. I'm showing it as a MOSFET, really, but this could be a bipolar, BJT2. So if this is R1, this is R2, and this is R3, right? If you're concerned about the transistor capacitors, to first order, if you have a 3-terminal device, there are 3 capacitors that you could be concerned about, right? There could be a C, what we call C pi here. There could be a C mu here. And there could be another capacitor which I call C theta. Right? So these are the 3 ways this capacitor can be connected around the 3-terminal device, right? There's no other combination. So what we will do, I mean, you've done this already, so I'm going to just write the result down, is that we have already calculated what the resistances are seen, that are seen across these 3. And now if you know those, and if you memorize them, and they're not that difficult to memorize, what they do, they will help you to actually determine these things much more rapidly, right? You can just basically go and quickly calculate them. So let's write them down. Is r pi 0 is r pi parallel, what you see, that sum of these two, r1 plus r2, divided by 1 plus gm r2. That's that resistor. Sorry. That resistor appears somewhere else. That's the r left for r mu. Now, and then r mu 0 is what we call r left plus r right plus capital GM, the effective GM, r left, r right. And what are these 3? R left is the resistance you see looking to the left, which is basically to the left of C mu, which is the resistance between this node and ground. What is the resistance between this node and ground? It's the resistor that I wrote earlier, which is basically R1 in parallel with R pi plus 1 plus beta R2. Right? Because if you think about what is the resistance between this node and ground, is R1 on this side, and you see whatever you have here, R pi plus 1 plus beta R2. Now, if it's a MOSFET, this part is infinity, if it's a classic MOSFET. So you will end up only with R1. And now R right is what? R right is the resistance you see on this side. In this case, it's just basically R3. Right? If you had an RO here you wanted to take into account, you say it's whatever output resistance of this thing is. This would be RO times 1 plus GM R3. Right? In most of these calculations, we drop RO, because usually you're dealing with smaller resistors than RO. But again, if you want to take that into account, you can take it. And then if you have, and the third resistor, which is R theta 0, is approximately, if you assume it's a large beta, is going to be this resistor plus that resistor scaled by 1 plus GM R2. Oh yeah, I forgot to mention that too. Okay, and this big GM is the GM of the transistor scaled by 1 plus GM_R2, which you can also write as 1 over Rm plus R2. Yeah, thank you. So these are the 3 parameters that goes in there. So what you do, you have for C mu, which is the longest one, is the R left, which is the resistance on the left side connected to its left side to ground, plus R right, which is the resistance on its right-hand side to ground, plus GM, effective GM, which is this thing, times the product of the two. And you will see, I mean, in practice, these are relatively easy to calculate when you get to it. So these are useful things to remember and know. And they are helpful because they allow you to calculate these things rapidly. So let's go back to our examples and do a little bit more analysis. So this was the transfer function, right? We calculated it. We saw that it has a pole and 0 at high frequency. So what we understand from this is that, at least based on this model, this stage, this follower stage, is a high frequency stage. It can handle high frequency transfer function. Now, how about its output impedance? That's another important parameter, right? We want to see how its output impedance behaves. Now, how do we calculate its output impedance? If you look at the stage again, if you look here, for example, the output impedance you're looking at is clearly, if you're looking at this output, or here, right, or out, you can clearly see it consists of two elements, two components, right? R2, looking down, and whatever you look up, you're looking up, you will see, right? When you look up through the source, what is this impedance that you see here? So we can, you always make your life easier. If you want to do these things, you can do it as a full, or you can say, look, I know it's going to be R2 in parallel with whatever this is, so let's calculate that whatever it is first, and then we say whatever the output total resistance is, the parallel combination of those two. So how do we do that? We need to find the output resistance of this thing. So let's draw this circuit. So what we are trying to calculate is the output resistance of this circuit. With that capacitor in place. Just for now, we are doing first order. So what do we see? So we are interested in what we call it R out prime. Then it would be total R out would be that in parallel with R2. Okay, so what is that resistance? Again, or in general, let's say Z out. So this is what we are calculating, Z out prime. So what is Z out prime? Well, how do we calculate it? It's the same deal. You're trying to calculate a transfer function. This time the transfer function is what? Is the ratio of the voltage of this port to the current of this port. So if you're trying to calculate an impedance, how are you really driving it? If that's the definition. How are we driving it? A current or voltage source specifically? If I'm trying to calculate an impedance, am I driving it with a current source or a voltage source? What is the impedance? The ratio of a voltage to a current, right? So the source, the stimulus, is the current. It's in the denominator, right? So it has to be a current source. This is important now because it will affect the time constants. And if you don't do it the right way, it's fine. You can say, I'm calculating, you can apply a voltage source here. But then you will be calculating an admittance. And if you do it correctly for the admittance, you will get also the correct result. But if you start switching around, kind of like from one to the other in halfway through, then you will get into wrong results. So if you're calculating an impedance, you're really driving it with an IX and measuring a VX. And what you're doing, you're really calculating the impedance by calculating that, and that's fine. So what are we calculating? So let's find out. There are three things we need to calculate, like any transfer function, right? We need the Z0, or Z pi 0, really. Oh, no, sorry, not Z pi 0. Z0. What is Z0? It's the output impedance when the element is zero valued, meaning the capacitor is open circuited, right? What do you see looking into this when the capacitor is not there, essentially? What is the output impedance when the capacitor is not seen? If it's a MOSFET, what would you see? Do you see the effect of R1 at all? No, right? Because that current is zero. So in other words, another way to think about it is that beta is infinity. You remember the reflection rule? We could take stuff from base to emitter and divide them by beta. So if you divide it by infinity, it's going to be 0. If it were a bipolar transistor, what would you see? You see alpha Rm plus R1 divided by 1 plus beta. Okay, so we know what it is. Let's keep things simple for now. So what is Z0? If it were a MOSFET? Rm. Right? What is Z pi? This means that the element pi, which is C pi, is infinite valued, meaning short circuited. So what is that? What do you see looking from the output if that's short circuited? R1, right? Is it clear? Did you see R1? Because this is short circuited, this current source becomes open because IS is 0, and then you see all you see is R1. So you see R1. And then, so you can see the calculation is pretty straightforward now, right? And then the last thing you need to do is to calculate its R pi, R pi 0. This is not necessarily the same thing as that because it's a different network now. We've changed it, right? We have to calculate this again. But it's pretty straightforward. So what is the rule for calculating that? You null all the independent sources. So when you null the source, what happens? You're open circuiting it, right? It's not there. So what do you see? What do you see looking across here? What does C pi see? Just Rm, right? Because there's no other path for the current to flow. Whatever you apply here, if you apply Vx, you will induce some sort of an Ix, but all of that current has to circulate through here. If you remove replace the capacitor with a test voltage or test current, you can see that easily. So it has to be Rm. So you can see that these are pretty straightforward calculations, right? So now if that's the calculation, what is the Z of S? Well, it is Rm plus R1, Rm times R1 times C pi, right? S divided by 1 plus Rm C pi S, right? Do you see this? Look at that equation if it's challenging. It's this thing. Instead of H0 we use Z0, instead of H1 we use Z1, and tau is basically R0 or R pi 0 times C pi, right? And then of course you can factor Rm, and what you're left with is something like this. R1 C pi S divided by 1 over Rm C pi S. So how does this behave? You have again a pole and a 0, right? Both of them are left half plane. We could have actually told they are left half plane by looking at the sign change of the H1 and H0, and we'll get to that in a little bit more detail in a second. But that's what it is, right? So what do we have? What is the transfer function? How does this look versus frequency? If I do a Bode plot of Z of j omega log of that versus delta omega or log of omega naught, right? What does it look like? Well, you have a pole and you have a 0. Which one happens first? Which one happens first? Well, it depends on the relative value of Rm and R1. Typically, if this transistor is properly biased, R1 can be large. If R1, let's say, is larger than Rm, and this doesn't have to be necessarily the case, what happens? Let's look at that, and then we can look at the other part. If R1 is greater than Rm, what do you start with at, right? You start at which one? If S is 0, you start at Rm, right? At 0 frequency, you start at Rm. So your transfer function starts over here at Rm, well, 20 log of Rm, but I'm just going to show it as Rm. And then if its R1 is greater than that, it's going to go to some other value, R1, right? Because at infinity, when S goes to infinity, you can see this reduces to R1 over Rm. Rm cancels, you get R1, right? So you go from a lower value to a higher value like this. Because this is where you have your, basically that's another way of saying that you have a 0 first and a pole next, right, in that transfer function. Now, what is the element that whose impedance increases with frequency? Inductor, right? So if that condition holds, if you have an R1 that's greater than Rm, in this range, it looks inductive. So a lot of times you may hear that the output impedance of a source follower or a common or emitter follower is inductive. That's what they mean. And this condition needs to hold. Because the other possibility is, so let's make it like this, color-coded, R1 greater than Rm, right? The other possibility is that, for example, Rm is greater than R1. Right? And if that's the case, what do we have? Well, then the opposite will happen, right? Because then this is going to go like whatever Rm is. It's going to go to a different R1, right? And now, how does it look like? It looks capacitive. So this is essentially a function of this thing, but this happens a lot of times. The way you pick values and all those things, that R1 is greater than Rm, because if you are using a proper transistor, you basically have a reasonably low Rm, which means that basically you want to have a large GM. Now, but if you don't have a high enough GM, this may not happen. So it looks inductive. That's what it tells you. Okay? Now, you can actually even try to estimate what that inductance is. Right? How do we estimate that? Well, can we think of something that models this behavior, something that looks like that? A network, a network consisting of passive devices that would behave that way, quantitatively. Or at least first qualitatively, let's say. So qualitatively, you want something that starts like the red one, right? I mean, it's something that increases. So you want to start with something that has a certain resistance, then it goes to a higher resistance. How can we make that? So we want something, one resistor, that is, let's say, if I take one resistor and then put it in parallel with an inductor and another resistor, what would this transfer function look like? What would this equivalent circuit look like? Let's call this RA and RB. What is this impedance like? It starts at RA parallel RB, right? And then it ends at RA, right? Because at very high frequencies, this becomes open. At very low frequencies, this is short. Right? At very low frequencies, this is short, so these are in parallel. At very high frequencies, this is open, so you just see RA. And the parallel combination is going to be smaller than 1, so you get something like this. So qualitatively, at least, there's something that behaves that way. So the question is, can we match these two to some accuracy quantitatively? Is there a way for us to quantitatively match these two? Right? So how can we do that? So let's find out what the output resistance, the transfer function of this thing looks like, right? The transfer function of this thing, so let's see if I can map it to that transfer function. Let me rewrite that transfer function here, that impedance. The impedance we are trying to match this to is Rm 1 plus R1 C pi S divided by 1 over Rm C pi S, right? So, and it goes from Rm here to R1. So from this, you can easily see what Ra needs to be, right? What's Ra? For them to match. It's R1, right? So we know Ra is R1. How about RB? Well, we need to make an assumption here. And the assumption we make, so to make it, I mean, you can calculate it exactly, right? If you calculate it exactly, you can put these things in there and do the calculation. So the calculation gives you RB is Rm. If you can write the parallel combination, it's going to be Rm times Ra over times R1 over R1 minus Rm. Okay? So that's that. So you can write it exactly like this. But if, for example, if now R1 is much greater than Rm, then you can actually ignore this thing, so it becomes roughly Rm. right? It's a simple algebraic first, one equation, one unknown thing to solve. So you do that, and you get this RB equals Rm. So now you have these two. The question is, what is the inductance, right? How can we calculate the inductance? Well, what is the inductance? What is this transfer function now if we have these two? So we said that this is Rm, Rb is Rm, and R is R2. So we can, let's say, if we make this R1, let me just use a different color. So let's say this is R1, and let's say this is roughly Rm. So what is L? Because we want to see what is the equivalent inductance, right? Because you can say, oh, this is the inductance of the output, and then you can change your parameters. You can actually even change that inductance. You can actually get something that, from a purely capacitive thing, and a transistor, you can get something that looks inductive. So that could be a useful thing. But anyway, how do we do that? Well, we write the transfer function of this thing, right? The transfer function of this thing, if you write it, approximately, it is the Z equivalent. Okay, let me just write it from here. So you can easily write the transfer function of this thing to be let's call Z equivalent of S. It's going to be approximately Rm times 1 plus L over Rm S divided by 1 plus L over R1 S. So we look at this and see if it matches this guy, and if you can find the answer to what the parameters are. So what should L be? Is there an L that satisfies both the numerator and denominator in this? Yeah, let's solve this, right? I mean, let's solve the numerator. So if you solve for the numerator, it says basically L over Rm has to be R1 C pi. Therefore, L equals Rm R1 C pi. And now if I plug this into here, what do I get? I get Rm C pi, which is this one. So it satisfies both the numerator and denominator. So that is the L. That's the inductance. The equivalent inductance, L equivalent. It means that the output of this stage, if R1 is much greater than Rm, is going to look like an inductor of this value. So in fact, by just choosing the values of Rm and R1, you can actually tune it to look like an inductance that you want. And this is one of the reasons, so if you use this stage, many times what you will see is that if you, for example, have a stage like this, driven by some source, and it drives some capacitive load, which could be the input of the next transistor, the input capacitance of the next transistor, you look at this node and you will see the step response looks like this. Make it look better. You see ringing, for example. You can see ringing. Although there's no inductance, no explicit inductance, looking into here you will see an inductive impedance. And that can result in ringing, which you can also use it to produce an inductive response if you need. You can make it some sort of a resonance made of that. Okay. Any questions on that? No? Okay. So let's do another example, just to get a sense. The other stage that we kind of like briefly talked about with C pi, but this time we will talk about C mu, is the common source, the voltage gain of a common source. So let me see. Let me just erase this. Open up some space here. So let's say now we are going to talk about a common source. We have an R1, and you have an R2 load. So you have V in and V out. And this time, let's just take into account the effect of C mu. That capacitance between CGD, or C, which we call C mu. So the question is that what would that do? What is the effect on this? Again, we can do this, but this time we will do it a little bit faster because we already have some of the key results and we are more familiar with this. So this is R1. This is going to be R pi in general. In the case of a MOSFET, it would be essentially a nothing, right? This is what we call V pi. Then you have the capacitor, you have the, I'm using the pi model here. GMV pi, you have R2. This looks like a pretty straightforward circuit, right? So now you have the C mu. We did the C pi version of this thing last time. So what is the, what do we get when we calculate this thing? What do we, what's the transfer function? So it's a V out and V O. So this is V out and V in. So let's do it quickly. So we need to calculate three things, right? What is the transfer function? So let's say H0 when the element is zero valued. What's the gain of the stage from the input to the output? If it's a MOSFET, there's no voltage drop here. If it were bipolar, there would be a voltage divider here, right? There would be an R pi, and then, so you have to calculate from here to there, which would be the voltage division, and then from here. But there's no voltage division here. So this V pi is the same as V in. So it's GMV pi current pulled out of R2, so this becomes negative GMR2, right? We've seen these kind of gains before. So this should not be surprising at all. Now, what is H1 when it's short-circuited? So now we need to short-circuit this and see what the gain is. So basically, this is short-circuited in this case. Or H should, actually, I should call it H mu, not H. I mean, to be consistent. H mu, not H1, which is H1. So what is that gain now? What do you see? So what is this? What do you see? What do you see here? If I have short-circuited these two, you have a current source whose current is proportional to its own voltage. Has another, that element has another name. A resistor, right? What is the resistance of that resistor? Rm. So what is this network like? This network looks like this. R1, Rm, R2. Right? So you're trying to calculate the gain of the transfer function of that thing. And that's pretty straightforward, right? You can say, let's write it this way. So it would be this thing divided by the total. So it would be Rm parallel R2 divided by R1 plus Rm parallel R2. You can also expand it. You can write it as Rm R2 divided by, let's not expand it for now. We'll deal with that later. So this is the H mu. There's one more thing you need to calculate, right? You need to calculate tau. It's really tau mu 0, but tau, we should show tau mu 0, but let's call it tau for now. What is tau? What is that time constant? Well, here we can use that general expression that we derived, right? We can use this thing because this is that capacitor. The only difference is that this resistor is not there. So my GM becomes my regular GM because this is 0. So this becomes capital GM becomes small gm, right? So what I need to do, I need to calculate the R left and R right. So what is R left? What is connected to the left terminal of this capacitor? When I null all the independent sources, what do I see to the left? R1, right? So let's say R0 or R mu 0 is R1. So that's R left, plus R right. What do I see to the right? I see R2, right? That's the only resistance I see. Plus R2, plus GM R1, R2. Right?
If you know the current source on the left, when you see...
The voltage source, you mean, on the left, right?
Oh, sorry. Okay. Yeah.
Yeah.
I got it.
Yeah, you got the answer. Yeah. Yeah, because the voltage source, it becomes short circuit. Yeah. That's okay. Yeah, so let's look at this now a little bit more. So let's expand it. So it's Rm over R2 divided by R1 Rm plus R2 Rm plus R1 R2, right? If you expand these things. And if you multiply it by GM, what do you get? You get R2 over R1 plus R2 plus GM R1 R2, right? Now, do you recognize this? The denominator? It's that thing, right? So we can simplify this as R2 over R mu, 0. I mean, these are just simplified algebra, yeah, just simplification. So if you do these three, then what is the transfer function? What is h of s? So h of s, you can write it in either form, but you can actually, if you write it in the factored form, which is the better form, it will be negative GM R2, which is H0. I'm factoring this one. Factored from this thing multiplied by tau. But tau is simply R mu 0, this guy that we calculated here, times C mu. So you will see that when you multiply this by tau, these guys cancel, right? So you're left with the R2 C mu. And you basically, and if you factor the R2 C mu and you factor the R2 and you've left and GM, negative GM, so you end up with negative GM over C mu. I'm sorry, negative C mu over GM times S, right? In the numerator. And in the denominator, you have 1 plus tau, so which basically is R mu 0 C mu S. Right. Right, so that's basically what it would be. Okay, so now what does that mean? What does it tell us? Let's look at these parameters. This is an equation. We need to make sure that we understand. So we obviously have a pole and a 0, right? Where is the pole and where is the 0? First of all, left half plane, right half plane. Well, the pole is left half plane, right? Because the root of the denominator is negative. The 0, however, is right half plane. So you got a left half plane pole and a right half plane 0. Right. Now, right half plane zeros are interesting characters because they introduce a fair amount of phase. Their phase behaves, their amplitude behaves like a pole, I would say like a 0. It goes up, but their phase behaves like a pole. So they introduce extra 0. But now, if you look at its frequency, roughly where is it with respect to Ft of the transistor? It's even higher than Ft because Ft was Gm over C pi plus C mu. And this is just Gm over C mu. So it's above Ft of the transistor. But it may still have some impact at some point. Now, how about its pole frequency? Let's talk about the pole frequency. Where is that? What's that doing? Where is that? Well, it's this guy, right? Now, if you look at these three terms and look at the most dominant term, which one is the largest component of these three? This one, right? Because it has an intrinsic gain multiplied by R1. Right? Because, not the intrinsic gain, the gain, Gm R2. So this is basically what's happening is that there's a larger resistor seen here. So if you look at it, it appears that the effect of this C mu is quite large because this resistance it sees is quite large. Right? And that's one of the important things that you can learn from this. And we'll discuss this. We will see that why this resistance is higher in a few minutes. But there is a reason why this capacitance is amplified, which is actually because of the Miller effect. Let me talk about Miller effect and what's happening there. Okay, any questions on this? All right.